Design and analysis of heat exchanger for determined heat transfer rate. Modification. Implementation of full baffle into the shell and tube heat exchanger. Modeling changes. Finding maximum inclination of baffle and creating various models with change the design of travel tube. Analysis. CFD analysis on 3D model in SolidWorks. Heat exchanger, as the name indicates, it transfers heat from one fluid to another which are at changed temperatures. Heat exchangers are devices built for efficient heat transfer from one fluid to another and are widely used in engineering processes. Some examples are intercoolers, preheaters, boilers, and condensers in power plants. The heat transfer efficiency depends on both design of heat exchanger and property of working fluid. Some important design parameters such as the pitch ratio, tube length, and tube layer as well as baffle spacing. In this project, the heat transfer efficiency is improved by implementing the full baffle design and travel tube design and analyzing it through CFD flow simulation to find the approximate heat transfer rates. From the simulation results, the optimum baffle design and travel tube design for maximum heat transfer rate is identified. Also, this project deals with find the suitable fluid for maximum heat transfer rate. Keyword CFD, heat exchanger baffle angle. Introduction. A heat exchanger is a device used to transfer heat between one or more fluids. The fluids may be separated by a solid wall to prevent mixing, or they may be in direct contact. They are widely used in space heating, refrigeration, air conditioning, power stations, chemical plants, petrochemical plants, petroleum refineries, natural gas processing, and sewage treatment. The classic example of a heat exchanger is found in an internal combustion engine in which a circulating fluid known as engine coolant flows through radiator coils and air flows past the coils, which cools the coolant and heats the incoming air. The order of reference in the running text should match with the list of references at the end of the paper. Shell and tube heat exchanger. A shell and tube heat exchanger. Shell and tube heat exchangers consist of series of tubes. One set of these tubes contains the fluid that must be either heated or cooled. The second fluid runs over the tubes that are being heated or cooled so that it can either provide the heat or absorb the heat required. A set of tubes is called the tube bundle and can be made up of several types of tubes, plain, longitudinally finned, etc. Shell and tube heat exchangers are typically used for high pressure applications, with pressures greater than 30 bar and 3 temperatures greater than 260 degrees Celsius. This is because the shell and tube heat exchangers are robust due to their shape. Several thermal design features must be considered when designing the tubes in the shell and tube heat exchangers. There can be many variations on the shell and tube design. Typically, the ends of each tube are connected to plenums, sometimes called water boxes, through holes in tube sheets. The tubes may be straight or bent in the shape of a U, called U-tubes. Shell and tube heat exchanger. Baffle design. Baffles are used in shell and tube heat exchangers to direct fluid across the tube bundle. They run perpendicularly to the shell and hold the bundle, preventing the tubes from sagging over a long length. They can also prevent the tubes from vibrating. The most common type of baffle is the segmental baffle. The semicircular segmental baffles are oriented at 180 degrees to the adjacent baffles, forcing the fluid to flow upward and downwards between the tube bundles. Baffle spacing is of large thermodynamic concern when designing shell and tube heat exchangers. Baffles must be spaced with consideration for the conversion of pressure drop and heat transfer. For thermoeconomic optimization, it is suggested that the baffles be spaced no closer than 20% of the shell's inner diameter. Methodology. Results. Solution for various inclined model are obtained and tabulated for comparison. Design and analysis. The shell and tube heat exchanger is designed on the basis of Tube Exchanger Manufacturing Association 1999 procedure. Design of exchanger. Pitch type is taken as 6-0 triangular to utilize the baffle space effectively. These design values and procedure are taken from the base paper Heat Transfer Enhancement of Shell and Tube Heat Exchanger. Model of heat exchanger. Analysis parameters. Fluid, water. Heat exchanger, material, stainless steel 321, counterflow shell and tube exchanger. Initial temperature, hot fluid equals 90 C, cold fluid equals 260 C. Flow rate, hot and cold fluid equals 0.0027 M3/S. Environmental condition, 270 C, 1 atm and heat transfer coefficient 5W/M2K. Temperature distribution, straight baffle with uniform tube. Various design approaches for tubes. Analysis of tubes. Heat exchanger parameters taken for analysis. Analysis of angled tube min and max temp values. Analysis of heat exchanger by adjusting baffle arrangements. Coolant fluid. A coolant is a fluid which flows through a device in order to prevent its overheating, transferring the heat produced by the device to other devices that utilize or dissipate it. An ideal coolant has high thermal capacity, low viscosity, is low cost, and is chemically inert, neither causing nor promoting corrosion of the cooling system. From various research journals, here we selected CuO nanostructures mixed with water as a coolant for max heat transfer rate. Properties. CuO nanostructures. Heat exchanger straight flow tube was replaced by combine of angle and step tube. It gives good thermal transfer capacity compared old straight tube and other designs of tubes. It was obtained by computational flow analysis. Baffle arrangement modifications also decides the heat transfer rate. The analysis carried out for making it inclined to the flow of hot fluid in the way of 5-0, 10-0, 15-0, 20-0, 25-0, 30 and 35-0. 9 results. Final analysis. From the baffle arrangement flow analysis results, the 350 inclinations of baffle gives good heat transfer rate comparing other inclination angles. CuO nanoparticles was selected as a coolant fluid which was added with water and used as a coolant medium. CuO nanoparticles was cheap and easily available. Also from the latest research results, copper. The flow simulation analysis is carried out for various baffle arrangement heat exchangers and maximum heat transfer angle of the baffle arrange was found by result comparison. From the comparisons of the result 350 baffle arrangement gives better heat transfer results. For maximum heat transfer rate the flow tube design was changed and best design was found by multi-model optimization method. From the basic flow analysis results the angle and step tube combined design was gives maximum temperature drop results. So that type of flow tube was selected. From the latest journals coolant fluid was selected as a CuO and water and their properties were given while making the final analysis of heat exchanger. Finally the baffle was attached with our selected flow tube and placed inside the heat exchanger and analysis was carried out. From that analysis result temperature drop of the working fluid, water, is obtained and which was gives good results over previous results. Inlet temp of working fluid, 90 C. Outlet temp of the working fluid, 41.3621 C. Coolant inlet temperature, 260 C. Coolant outlet temperature, 68.321 C. Final result discussion.